Hi, my name is Eva Martino, and I'll be presenting on Lab 3 of Physics 2212 Circuits. In the introduction, I'll outline the purpose of the lab and introduce some key concepts used during the experiment. Next, I'll go over some of the predictions and answer the questions of the experiment. I will then go over calculations needed to find the current in RC. Finally, I'll address the what-if discussion questions. The purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and in parallel, and examine the behavior of ohmic resistors and capacitors. In this experiment, the system is the circuit and its components, while the surroundings constitute everything else. A preview of the results, the current for the first part is equal to about 0.02 amperes, and the RC for the second part is about 5.88 seconds. Some key components used during the experiment are the node rule, which is the total current entering an anode in an electrical circuit must be equal to the total current leaving that node, and the loop rule, which is the sum of all the voltage changes around any closed loop in an electrical circuit is 0. And finally, Ohm's law, which describes the relationship between voltage, current, and resistance in an electrical circuit, which you can see at the bottom. So starting off with the predictions, for the first part of the lab, we need two 1.5 volt batteries, 2 ammeters, and one 47 ohm resistor and one 100 ohm resistor. You can see my prediction calculations on the side of the slide where I use the delta V is equal to the current times the resistor. By solving for the unknown, I got 0.0204 ammeters. To find the actual, I allowed the computer model to run and read the number from the ammeters and applied the node rule, which was approximately 0.02 ammeters. So moving on, I inserted one of the ammeters backwards to test whether this would change our answer, and I found out that it does not affect the current. Next, I replaced the ammeter with a voltmeter. This changed our answer from 0.02 to 0 because there is no current running through the circuit because the circuit is not complete. Next, we had to perform some calculations to find the potential difference, so I connected a voltmeter between each segment to find the voltage. Only 3 sections had a non-zero voltage, which were sections A to B, C to D, and E to F. When you add all of these voltages together, you get a number somewhere near 0. Next, we had to calculate the effective resistances. So for this, we used one of the ohmic law's equations. R is equal to delta V divided by I, and I is equal to delta V divided by R. Ultimately, we found that the effective resistance is 0.06 amperes. So now moving on to part 2, here's what my model looked like. On the left, you can see the circuit where the battery and capacitor are connected. The battery charges the capacitor until it is full and lights the bulb. For the image on the right, the capacitor is the one that lights the bulb until it eventually is fully discharged and the light dims and eventually is off. Here's a graph of my results. The graph is a natural log of voltage divided by initial voltage versus time graph. I numbered the time from 0 to 20 seconds and used the voltmeter to read the voltage during each second. Then I put in a calculation for the natural log on the right column and created my graph. Next, we had to predict the RC using the resistance of the light bulb and the 0.2 capacitance, giving us approximately 6 seconds. To find the observed RC, we used the negative reciprocal of the slope, which gave us 5.8824 seconds. Now, some errors that could have occurred are human errors such as miscalculations or rounding errors, or the model may not have been as accurate as a real-world scenario. Now, what if you were doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? A real ammeter has resistance, so the total resistance increases slightly, causing the voltage to drop. Now, what if you were doing this experiment in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So, our ideal model would predict the capacitor would charge instantly. However, this would not actually occur because in real life, real components have resistance. So while it may be quick, it would not be instant.